Good morning, dear colleagues, all participants and organizers of the conference. My name is Ekaterina Fedorova, and my co-authors are Anatoly Nazarov, Olga Lizura, and Radmir Salimzyanov from Tomsk State University. And we're glad to present you our scientific work, Asymptotic Diffusion method for a retrial queue with state-dependent service rate. Retrial queues is non-classical queuing models which applied for in communications system, networks, nodes, call centers, economic system, etc. The main feature of the retrial queues is absence of classic queue, but there is a virtual place where unserved customers waiting a random time, and this place is named as orbit. Let us consider the following single server retrial queue. Calls arrive in the system according to the person arrival process with rate lambda. If a call finds the server free, it starts the service with exponential distributed service time with rate mu I. If a server is busy, the call goes to an orbit where it stays during random time distributed by exponential law with rate sigma. After the delay, the call makes an attempt to get service again. And if the server is free, it starts the service, and in other way, it instantly returns to the orbit and make next attempt. The significant difference of this considered in this paper model is the variable service rate mu I. It depends on I of t, the number of calls in the orbit at the moment t. For presented notations, we write Kolmogorov Equations 1, and we proposed the asymptotic diffusion analysis method for the system 1 solving. These methods consist of two steps: first order asymptotics and second order asymptotics. First of all, we choose the limit condition of a long delay, so the rate sigma goes to 0, or we write sigma as an infinitesimal value epsilon. Using notation presented in this slide, we obtain asymptotic equation system and making some transforms and expand function in series, we finally get system equation 2 with finite parameters. Then we make a second order asymptotic analysis and use following notation presented in the slide. So I don't show all math transformations which we make for system 5, but only final results. We write the undefined function as sex, and then we obtain some expressions for undefined parameters. All formulas presented in the slide, and finally we have we obtain Fokker-Planck equation for probability density function P of y tau. And rates of this equation we also obtained. As a result, asymptotic diffusion methods, we introduced stochastic process, which defined by Fourier-Planck equations 10, and in steady mode, for example, we can write formula 11 for our process z of 10. For calculating asymptotic probability distribution of number of calls in the orbit, we need to write discrete distribution in the following way as example. So for demonstrating the proposed method application area, we present some numerical examples of comparison of the asymptotic and simulated distribution for some values of the model parameters. In this slide, we present the comparison for linear function of mu of x. The left picture is for sigma equals 1/10, and right one is for sigma equals 100. Also, we consider exponential law of mu of x and calculate Kolmogorov distances for different values of system parameters. As you can see, the method is enough accurate for sigma less than 1/10. Also, we show the dependency of the asymptotic result for different values of lambda, and also we have obtained good accuracy of approximated method. One more example presented in the slide is for the following function of mu of x. It is interested that in this way, for lambda equals 97th of 100th, we have stationary retrial Q. But already for lambda equals 1, there is no stationary mode, the system in non-steady state. It is this situation described by different values of parameters, coefficients of drift in Fourier-Planck equation A of x. So we conclude that if f A of x is positive, then the system is in a non-stationary mode. If equation f of x equals 0 has one root and this function decreased, the system is in steady state region. And also there is an interesting situation when this equation has two roots, then system is non-stationary mode, but there is a pseudo-steady state period in some values. So in this way we consider retrial Q with state-dependent service rate and proposed asymptotic diffusion method for it studied, which has a good accuracy of approximation. So in future we plan to apply this method for non-Markov retrial Qs, for example, with non-Poisson arrival process. Thank you for your attention.